This question is being answered for the benefit of one of my grade 12 classes because I did this question incorrecly. So I redid it and I'm posting it for your benefit. This is question 1522 from your textbook. Again, it's from Brown, 10th edition. The first question from the book shows you the equation and it gives you the Kp for that equation at 480 degrees Celsius. And they ask, what is the Kp for the reverse reaction? Well, the rule is that when you reverse the reaction, you take the reciprocal of the forward reaction. So 1 over Kp is 1 over 0.0752, gives you 13.3. Then they ask, what is the K for the value, the K value for the reaction multiplied by 1/2? So you take this reaction, multiply the whole reaction by 1/2, you will get this reaction. The rule says that when you multiply a reaction by 1/2, you have to raise the value of K by the same number. So we're going to raise the K to the power of 1/2. So we're going to take the square root of K. 0.0752 raised to the power of 1/2 gives you 0.274. And lastly, they ask for the value of Kc from the Kp. So you have to use Kp is equal to Kc RT raised to the power of delta N, where delta N is the difference between the moles of gaseous product minus the moles of gaseous reactant. You have 2.5 moles of product, 2 moles of reactant. So the difference is 0.5. 2.5 minus 2 gives you 0.5. So we entered in the values. The value of R is 0.0821 liter atmospheres per Kelvin mole. Temperature is in Kelvin. Kelvin cancels and we get an answer in liter atmospheres per mole. But we typically don't include units when we report values of K. And the final value is 3.48 times 10 to the minus 2. In the second question that I did yesterday, it's an example of how we use an IREC table. I've already mentioned how we use an ICE table. This is how you use an IREC table where they report amounts, but without giving the concentrations. So we were told initially that a reaction contained 0.566 grams of hydrogen, and that it ended up with, the reaction starts off with 1.374 grams of hydrogen and ends up with 0.566 grams of hydrogen. So these are the two initial states. That's what we're given at the beginning. And I've converted these gram amounts into moles. This is what I did here, 1.374 divided by the molar mass of hydrogen gas, which is diatomic. That's why I'm saying 2 times 1.00794 is 0.68 moles of hydrogen. At the end of the reaction, so I put that in the initial for the IREC table. At the end of the reaction at equilibrium, we're told there's 0.28 moles of hydrogen gas. What is 0.28 moles? It's the 0.566 that's reported here. So the difference between the initial and equilibrium conditions allows me to calculate how much reacted. In the last step, the C, I simply divided the equilibrium amount of hydrogen by the volume of the reaction vessel. So that's how we get the concentration of hydrogen. That's what makes the IREC table useful. It's for when the initial conditions are in moles or grams, which you then enter as moles. The ICE table is instead used for when you have concentrations at the outset or partial pressures. The bromine amount was 70 grams divided by the molar mass of bromine. Recall that bromine is diatomic, so we had 0.43 moles of bromine. The stoichiometry of the reaction is 1:1, so if we use up 1 mole of hydrogen, we're going to use up 1 mole of bromine. That's why both these numbers are identical. I subtracted this from the original amount of bromine. That's how many moles of bromine are left at equilibrium. Divide by 2 to find the concentration of bromine. This is the one product that we have. There's none at the beginning. I add again this number, except I multiply by 2. Why? Because the stoichiometry is 1 to 2. This is our, how much the amount of bromine increases by. I should put minuses over here. Ooh, that's equilibrium. I should say plus over here. And I divide by 2 to find out the equilibrium concentration of hydrobromic acid. And then we calculate Kc the regular way. Products over reactants, put this to the power of 2. These two are to the power of 1. Enter in the equilibrium concentration, and we get a value of 58.5. We're only allowed 3 significant figures. This value is only 3 significant figures, so the final answer is 58.5.